I want you to just take a second and look around wherever you are right now. Look at your hands. Look at the room you're sitting in, or, look out the window at the sky.
Everything you see is temporary.
Right. Exactly. Everything you know, everything you love, every single memory you hold, every monument humanity has ever built, and literally the very light illuminating your world. It is all living on borrowed time.
From a physical standpoint, yes.
And I am not just talking about like the end of the Earth or the sun burning out in a few billion years. I'm talking about the expiration date of reality itself.
The ultimate boundary condition.
Yeah, the absolute final end of time, space, and existence. And that is exactly what our mission is for this deep dive.
We are examining the thermodynamic and cosmological termination of the universe.
Because today, we are looking at the ultimate fate of everything. We're going to track the math and the physics, from the agonizing slow starvation of the stars to the violent shredding of space-time.
And we will conclude with a fairly recent theoretical framework from the last couple of years that suggests...
Oh, this is the part that keeps me up at night.
It suggests the universe we are observing might already be a deceased structure.
A corpse. A literal cosmic corpse. So, for our stack of sources today, we are pulling from foundational astrophysics papers on the 5 ages of the universe. We're looking at theoretical models of cosmological doom, like the Big Rip and False Vacuum Decay, and that newly published framework from 2024 to 2026 known as the Dead Universe Theory.
The underlying physics across all of these models, regardless of how divergent their conclusions might seem, are governed by the same fundamental mechanics.
Which are?
Energy dissipates. Entropy increases. From a purely thermodynamic perspective, the universe you are observing right now is simply a machine.
A machine that's breaking down.
A remarkably complex machine, yes, but one that is irreversibly running out of usable energy. It is a closed system marching steadily, mathematically, toward absolute equilibrium. Complexity is a temporary, highly unstable state of affairs.
You say that so calmly, like complexity is temporary. You're talking about the erasure of everything.
It is simply the data.
Well, this deep dive isn't just a physics lesson, okay? It's a look into our ultimate execution. And frankly, some of the math we're going to get into today is just pure existential terror.
Fear is a biological response to a loss of energy gradients.
That is the most astrophysicist way to describe dread.
Yeah.
So look, to understand how we die, we first have to understand the default trajectory.
The baseline.
Right. If nothing unexpected happens, how does the universe naturally wind down?
Before we examine the more violent or abrupt cosmological conclusions, we must establish this baseline, which is dictated by the second law of thermodynamics.
Which goes all the way back to the 1850s, right?
It does. This realization stems from the work of William Thomson, who is more commonly known as Lord Kelvin.
The Kelvin temperature scale guy.
Precisely. Kelvin realized that the universe is inevitably marching toward a state known as thermodynamic equilibrium.
The heat death. Which, I have to say, is a terrible name.
It is often misunderstood by the public, yes.
Because it sounds like we all burn to a crisp, like the universe becomes an oven.
Exactly, but heat death does not imply that the universe burns up. In physics, it means the exact opposite.
It means it freezes.
It is a state where all energy is completely uniformly distributed across the expanding volume of the cosmos. To understand this, you really have to understand what entropy actually is.
People usually say entropy is chaos or disorder.
That is a colloquial simplification. Entropy is fundamentally a measure of the number of possible microscopic arrangements of a system. Systems naturally evolve toward the state with the highest number of arrangements.
Which is total uniformity. Everything's spread out evenly.
Yeah.
Okay, let's unpack this for a second. If I have like a hot cup of coffee in a cold room, there is a temperature gradient.
A difference in potential.
Right. There is a difference between the coffee and the air.
Correct. And because of that gradient, energy flows from the hot coffee to the cold room.
Heating up the room slightly.
And cooling the coffee. Work can be extracted from that flow. You could theoretically run a tiny heat engine off that temperature difference.
But eventually, the coffee and the room become the exact same temperature.
Thermodynamic equilibrium. The energy hasn't disappeared. It is still there, vibrating in the air molecules of the room, but it is no longer usable.
Because there is no gradient anymore.
Precisely. Without a difference in temperature between 2 points, no thermodynamic work can be performed. No engines can run.
No stars can ignite.
No biological processes can function. Heat death is the cosmic equivalent of the coffee matching the temperature of the room. It is a state of maximum entropy.
So to really grasp the sheer crushing scale of how long it takes for the entire universe to reach room temperature, we need to look at Fred Adams and Gregory Laughlin's concept.
Their foundational paper on the 5 ages of the universe.
Right. And they don't measure time in years, or even billions of years, because those numbers become completely meaningless almost immediately when you talk about the cosmos dying.
Normal chronology fails us entirely here. You cannot use standard notation.
So what do they use?
They utilize a logarithmic chronology known as the cosmological decade.
Okay, break that down for us.
In this system, each cosmological decade, which is denoted by the variable n, represents 10 to the power of n years after the Big Bang.
So it's exponential.
It scales exponentially. The first cosmological decade, where n equals 1, is 10 years. The second, n equals 2, is 100 years. The third is 1,000.
So by the time you get to 10 to the power of 10, that's 10 billion years.
Correct. Which brings us to the first era of their model, the one we are currently residing in.
The Stelliferous Era, the era of stars.
Yes. According to the timeline, this era runs from cosmological decade 6 to 14.
So from 1 million years to 100 trillion years after the Big Bang.
It is characterized by active star formation, the existence of galaxies, and the synthesis of heavier elements in stellar cores.
Gravity pulls hydrogen gas together. The friction creates immense heat. Nuclear fusion ignites, and boom, a star is born.
It is an era of immense thermodynamic gradients.
Now here is where I have to push back on the astrophysics community a little bit. Yeah, because there is this concept you all use called the Copernican time principle.
The assertion that our current epoch has no special significance in the grand scheme of the universe.
Right, it's
Yes.
just another tick on the clock. But, I mean, from a biological, philosophical standpoint, this is the only era that matters.
To biology, perhaps?
Not just perhaps. This is the era of light, of warmth, of liquid water.
Yeah.
This is like peak life. This is the only window where we can exist to even have this deep dive.
Structurally, however, the Stelliferous Era is little more than a brief, fiery adolescence in the lifespan of the cosmos.
That is so depressing.
It is simply a transient, highly chaotic phase where the universe is burning through its primordial reserves of free hydrogen.
Like a fast-burning match.
Exactly. It feels significant to you because your biology is an artifact of these specific, localized temperature gradients.
Okay, ouch.
But astronomically speaking, the universe spends the vast, overwhelming majority of its existence in complete darkness. The era of starlight is a statistical anomaly.
A brief, fiery adolescence. That is incredibly bleak. And that transition into the darkness, that brings us to the first major extinction event on our timeline.
The ESME.
The Stelliferous mass extinction event. I want you to imagine this. Really picture it.
It will occur around cosmological decade 14.
Right. So you are standing on a rocky planet circling a red dwarf star trillions of years in the future. Star formation has entirely ceased.
Because the universe has run out of free hydrogen gas, there are no nebulae left to birth new suns.
One by one, the massive, beautiful blue stars died out billions of years ago. The yellow stars, like our sun, they followed.
Leaving only the low-mass red dwarfs.
Just these tiny, dim red dwarfs hoarding their fuel. And then the very last star in the universe burns through its final scraps of hydrogen. It flickers. It fades.
And nuclear fusion in the cosmos ends.
The lights go out. Forever. Planets go dark.
Yeah.
Entire biospheres freeze solid. It is the absolute end of peak life.
That thermodynamic exhaustion marks the beginning of the Degenerate Era.
Which sounds like a terrible party, but
Yeah.
it's actually just dead space.
It spans cosmological decades, 14 through 40. So from 100 trillion years to 10 duodecillion years.
I don't even know what a duodecillion is.
It is a 1 followed by 39 zeros.
Jesus.
In this era, the universe is no longer populated by luminous stars, but by their dead, degenerate remnants.
White dwarfs, brown dwarfs, and neutron stars.
Exactly. The universe will be a profoundly cold, sprawling graveyard of ultra-dense matter.
Just dead husks drifting in the pitch black, nothing happening.
Well, not entirely nothing. Even these husks are not eternal. Nothing is. This era is governed by a phenomenon that takes so long we have never actually observed it in a laboratory.
Proton decay.
Yes. Now, the standard model of particle physics suggests protons are entirely stable,
It lasts forever.
theoretically. However, grand unified theories, which attempt to unite the strong, weak, and electromagnetic forces, predict that protons, the fundamental building blocks of all baryonic matter, must eventually decay.
Wait, explain what that actually means. A proton is the core of an atom. You're saying the very building blocks of a rock or a dead star just fall apart.
Precisely. A proton is made of elementary particles called quarks. 2 up quarks and 1 down quark, bound by gluons.
Okay.
Grand unified theory suggests that over incomprehensible timescales, a quark can change its flavor via the emission of a superheavy boson and eventually cause the entire proton to decay.
Into what?
Into lighter subatomic particles like positrons and neutral pions. The pions then decay into gamma-ray photons.
So matter just turns into light and radiation. How long does this take?
The half-life of a proton is estimated to be between 10 to the power of 34 and 10 to the power of 42 years.
Wow. Okay, so if I'm looking at a dead frozen planet drifting in the Degenerate Era, what physically happens to it?
If proton decay occurs, that frozen planet will slowly dissolve. Every dead star, every asteroid, every monument humanity ever built, it will all decay from the inside out.
Just evaporating.
The solid matter will simply evaporate into free radiation. A slow, silent dissolving of all solid mass in the universe.
Oh, okay, what if they don't decay? What if the standard model is right and protons are actually immortal? Does the dead planet just float there as a rock forever?
No. If protons do not decay, the universe faces a different, equally bleak mechanism.
Of course it does.
Over exponentially longer time frames, we are talking cosmological decades stretching into the hundreds, matter will undergo quantum tunneling.
Okay, here's where it gets really weird. ELI5 quantum tunneling for us. Like, explain it like I'm 5. How does a rod change if it's sitting at absolute zero?
Think of a classical physics scenario.
Yeah.
If you have a ball at the bottom of a valley and it doesn't have enough kinetic energy to roll up and over the hill, it stays in the valley.
Right, it doesn't have the energy to climb the barrier.
But in quantum mechanics, particles do not have exact, definite positions. They behave like probability waves.
So they're sort of smeared out.
Yes. Because the wave function extends through the barrier, there is a vanishingly small but non-zero mathematical probability that a particle can simply pass through the energy barrier and appear on the other side.
Without needing the heat or energy to climb over it, it just teleports through.
Essentially, yes. So over trillions of trillions of trillions of years, the atoms in that frozen planet, or a white dwarf star, will slowly, spontaneously reconfigure themselves.
The atoms just sort of shift around.
Elements will fuse and transmute at zero temperature. Given enough time, all baryonic matter in the entire universe has a statistical certainty of quantum tunneling into the most tightly bound, stable atomic nucleus.
Which is what?
Iron 56.
So if proton decay isn't real, the universe just turns into giant cold spheres of solid iron.
Yes. Macroscopic, freezing iron stars. But ultimately, over even longer timescales, up to cosmological decade 10 to the power of 32,000.
Oh, the Lord.
Even these iron stars will succumb to their own minuscule gravity and quantum tunnel into black holes.
Which ushers in the fourth age of the Adams and Laughlin model.
The black hole era. Cosmological decades, 40 to 100.
The only macroscopic objects left in the entire cosmos are black holes. And this is where we have to talk about the ECME.
The end civilization mass extinction event.
Yes. It's literally the most desperate, terrifying image I have ever encountered in astrophysics.
It is a theoretical concept regarding incredibly advanced civilizations that have somehow survived the death of the stars.
Right, so picture it. You are part of an unimaginably advanced species. You've somehow outlived the Stelliferous Era.
You've survived the dissolving of planetary bodies in the Degenerate Era.
And now the only objects left in the pitch-black void of space are black holes. You and your civilization are clinging to the edges of an evaporating black hole,
Station just outside the event horizon,
trying to harvest the absolute last scraps of rotational energy through the Penrose process.
which is a mechanism to extract energy from the ergosphere of a rotating black hole.
You are huddling around the cosmic equivalent of a dying ember in a freezing blizzard. It's the last campfire in the universe.
And thermodynamics dictates that even that ember will inevitably go out.
Because of Hawking radiation.
Yes. In 1974, Stephen Hawking demonstrated mathematically that black holes are not completely black.
They glow.
Very, very faintly. Due to quantum fluctuations near the event horizon, black holes emit thermal black-body radiation.
I need you to explain this, because how does a black hole, something whose gravity is so intensely strong that not even light can escape, how does it leak radiation?
It requires an understanding of the quantum vacuum of space. The vacuum is not truly empty.
It's boiling, right?
Yes, it is a boiling soup of virtual particle-antiparticle pairs. They constantly pop into existence from the vacuum energy, annihilate each other instantly, and vanish back into the vacuum.
So space is constantly sparking with these ghost particles.
This is deeply connected to the Unruh effect, which shows that the concept of a vacuum actually depends on the observer's acceleration. An accelerating observer will see a warm background of radiation, where a stationary observer sees an empty vacuum.
Okay, so how does the black hole interact with that boiling soup of virtual particles?
When a virtual particle pair pops into existence exactly on the boundary of the event horizon, the immense tidal gravity of the black hole can pull one particle past the horizon into the black hole.
While the other particle?
The other particle escapes into space. The escaping particle becomes real, measurable radiation.
But wait, if it's emitting particles, where's the energy coming from?
From the black hole's mass.
Yeah.
To conserve energy, the particle that fell in must have negative energy from the perspective of an outside observer. This negative energy subtracts mass from the black hole.
Meaning the black hole is slowly evaporating.
Precisely. It is losing mass. And the mathematics of this evaporation are fascinating.
You brought the equation, didn't you?
I did. The Hawking temperature of a black hole is calculated as temperature equals the reduced Planck constant times the speed of light cubed.
Okay, h bar c cubed.
Divided by 8 pi times the gravitational constant times the mass of the black hole times the Boltzmann constant.
Okay, that is a massive equation. Let's translate that into English. What does it actually mean for our desperate civilization huddled around the black hole campfire?
The crucial takeaway from that equation is where the mass variable is located.
It's in the denominator.
Exactly. This creates an inverse relationship between mass and temperature. The more mass of the black hole, the colder it is, and the slower it evaporates.
So a big black hole is actually freezing.
A supermassive black hole with the mass of 1 billion suns is only a tiny fraction of a degree above absolute zero. It will take up to 10 to the power of 100 years to evaporate.
But because of that inverse relationship, as the black hole slowly loses mass over octillions of years, its temperature goes up, right?
Yes. As mass decreases, temperature increases.
This is the ultimate cruelty of the physics. Like, for those civilizations clinging to that black hole for warmth for billions of years, it's a freezing, agonizing existence.
Yeah.
Just trying to survive.
They would be starved for usable energy.
But in its final moments, as its mass drops down to the size of, say, a mountain, the math flips. The temperature increases exponentially.
The evaporation rate accelerates violently.
It doesn't just quietly fade away. It reaches billions of degrees and vanishes in a violently blinding, destructive gamma ray burst.
A massive explosion of hard radiation.
The absolute last heat sources in the universe are literal time bombs. You huddle around them for warmth, and then they detonate in your face.
It is an unavoidable thermodynamic consequence, which leaves us with the final state.
The Dark Era.
Cosmological decade 100 and beyond. Once the last black hole has detonated, the universe is essentially a void.
Nothing left.
It contains nothing but a staggeringly dilute gas of extremely low-energy photons, neutrinos, and the occasional electron or positron.
You mentioned something called a positronium atom in this era. I'm trying to wrap my head around it. What is that?
It is a highly exotic bound state. It consists of an electron and a positron orbiting a common center of mass.
A positron is the antimatter version of an electron, right?
Correct. Now, because the density of the universe is so incomprehensibly low at this point, these solitary particles will drift for trillions of years without encountering anything.
Just totally alone.
But when an electron and a positron do finally cross paths, their electrostatic attraction can cause them to enter a mutual orbit.
Like a binary star system, but with subatomic particles?
Yes. However, due to the extreme expansion of space and their incredibly low kinetic energy, the distance between them is vast. The diameter of a single positronium atom in this era could be larger than the size of our current observable universe.
Wait, pause. Hold on.
It is mathematically sound.
An atom, where the electron and positron are orbiting each other. But the distance between them is the size of our entire currently observable universe.
Yes, 93 billion light years across.
The sheer scale of the vacuum between them is staggering.
And this macroatomic structure is entirely unstable. The particles will slowly radiate away their orbital energy as very low-frequency radio waves.
So they are spiraling inward,
Very, very slowly. This inward spiraling will take unfathomable amounts of time, perhaps 10 to the power of 141 years.
Just to cross that distance.
But eventually, the electron and positron will collide and annihilate each other, releasing a pair of gamma-ray photons. And then, truly, nothing of consequence will ever happen again.
I want you to really visualize this because it absolutely breaks my brain. Imagine you are placed in a room. An infinitely massive, perfectly dark, freezing empty room.
The spatial metric at maximum entropy.
And somewhere in that room, someone turns on a single flashlight beam. But the room is so unfathomably huge that the beam of light takes trillions upon trillions of years just to cross from one side to the other.
And that is the only event occurring.
That is the dark era. So I have to ask, if absolutely nothing is happening, if there are no events to measure, no collisions, no gravity, no stars, does time even exist anymore?
From a strictly thermodynamic standpoint, no. Time, as we experience it, is intrinsically linked to entropy.
The arrow of time.
Exactly. The arrow of time, the reason time moves forward and not backward, is defined by the transition from a state of low entropy to high entropy.
Like an egg breaks, it does not unbreak.
Right. But when the universe reaches maximum entropy, when all energy is perfectly uniformly distributed, there are no more gradients.
No more hot and cold.
Without gradients, there is no irreversible process. Past and future become physically indistinguishable. The arrow of time effectively vanishes.
That is profound and entirely depressing. Time itself just evaporates because it has no reference points left.
It becomes a meaningless coordinate.
But, okay, the heat death assumes that the universe just slowly coasts to a halt over octillions of years. It assumes a passive fading universe.
It relies on dark energy remaining a stable cosmological constant.
Right. But what if the very fabric of space isn't passive? What if dark energy changes? What if gravity wins? Or what if the expansion turns hostile?
This brings us to the violent alternatives.
Let's get into it.
Let us first address the scenario where gravity reasserts dominance. The Big Crunch.
I've always thought of this as the universe hitting the rewind button.
Functionally, yes. The theoretical foundations for this date back to 1922, derived from Alexander Friedmann's equations.
Which are based on Einstein's relativity.
They are exact solutions to Einstein's field equations. Friedmann's equations demonstrate that the geometry and ultimate fate of the universe depend entirely on its density.
The amount of stuff in it.
Matter and energy, yes. There is a critical threshold. If the average density of the universe exceeds this critical threshold, the gravitational attraction of all the mass in the cosmos will eventually overpower the expansion driven by the initial Big Bang.
So gravity acts like a giant bungee cord.
The expansion of the universe would slow, halt, and then the metric of space itself would begin to contract.
The visualization of this is pure terror. Like, if the universe starts shrinking, all the light that has been emitted by every star over billions of years gets compressed.
The photon density increases dramatically.
Space gets smaller, so the wavelengths of light get squished. The sky doesn't get dark, it gets unimaginably bright. It blue shifts.
The cosmic microwave background radiation would also compress.
Right, which right now is just a faint, freezing, cold static left over from the Big Bang.
Yeah.
But in the crunch, it gets compressed and heated up. The sky literally becomes a blinding, infinite oven.
A high-energy plasma state.
The radiation intensifies so much that it ignites the surfaces of stars before they even physically collide with one another. Stars would cook from the outside in.
The thermodynamics of the contraction phase are indeed catastrophic. The energy density of the universe would approach infinity.
Everything just piles up.
Everything, all matter, all radiation, all biological life, and the very fabric of space-time itself would collapse into a dimensionless singularity.
Recreating the Big Bang.
Essentially recreating the exact conditions of the Big Bang, but in reverse. However, I must interject with the observational data here, which makes this scenario highly improbable.
Oh, thank God. You're going to tell me we're safe from the giant space oven.
We are safely below the critical density. The most recent data from the cosmic microwave background, provided by missions like the Planck satellite, along with observations of distant type Ia supernovae, show conclusively that the expansion of the universe is not slowing down.
It's speeding up.
It is accelerating. The overall density of the universe is far too low to halt the expansion. A big crunch is highly unlikely based on our current cosmological parameters.
Okay, so we don't get crushed. But the acceleration you just mentioned, that leads us to the second violent alternative. And honestly, this one is my absolute worst nightmare.
The Big Rip.
The Big Rip. It sounds like a bad sci-fi movie, but the math is terrifying.
It is a cosmological model heavily dependent on the exact nature of dark energy. Currently, in our standard lambda CDM model, dark energy behaves like a cosmological constant.
Meaning it doesn't change.
We measure this using an equation of state parameter, denoted by the letter W. Right now, observation suggests W is equal to -1.
Okay, what does W equal to -1 mean for space?
It means the density of dark energy remains perfectly constant, even as the universe expands. A cubic meter of space today has the exact same amount of dark energy as a cubic meter of space had 10 billion years ago.
So regular dark energy is like a car driving at a steady speed. It's pushing space apart at a constant rate.
A fair analogy.
But what if W is less than -1?
If W drops below -1, we enter the regime of what physicists call phantom dark energy.
Phantom energy.
In this scenario, the density of dark energy does not remain constant. It actually increases as the universe expands.
So phantom dark energy is a car where the accelerator pedal is stuck to the floor, and the engine is revving so hard the chassis is starting to vibrate apart.
The kinetic energy of the expansion grows unboundedly.
As space expands, the energy pushing it apart gets stronger, which makes it expand faster, which makes the energy even stronger.
Exactly. It creates a runaway feedback loop. The expansion rate of the universe accelerates toward infinity in a finite amount of time.
A runaway feedback loop that literally shreds reality. The timeline laid out for the rip is so visceral and escalating. I want to walk through exactly what this looks like because it is terrifyingly specific.
The mathematical models of phantom energy allow us to calculate the precise moments when various cosmic structures become unbound by the accelerating expansion.
We can map out the doom.
Assuming a specific value for W, yes. The fundamental scale factor of the universe eventually overpowers all other fundamental forces.
Right. So let's say we are counting down to time 0, the exact moment of the big rip. Walk me through the timeline.
200 million years before the end, the phantom energy becomes so powerful it overpowers the gravitational binding of galaxy clusters.
The largest structures in the universe fail.
The local group is torn apart. The Virgo cluster scatters into the dark.
Okay, so the big neighborhood breaks up. Then what?
60 million years before the singularity, the phantom energy overcomes the gravitational binding of individual galaxies.
Our Milky Way disintegrates. You look up at the night sky, and the stars at the edges of the galaxy are just pulled away. They drift off into the void at impossible speeds. The glowing band of the Milky Way across our sky literally evaporates. We are completely isolated.
3 months before the end, the expansion rate of space is so severe it overwhelms the gravitational pull of a star on its planets.
Just 3 months, the solar system unbinds. The Earth is ripped away from the sun. We just drift out into the freezing dark.
30 minutes before time 0, the gravitational binding of planetary bodies fails entirely.
The Earth explodes. The very crust beneath your feet splinters and is pulled up into the sky because gravity just ceases to function against the push of space itself. The planet is unmade.
At 10 to the power of -19 seconds before time 0, the expansion overpowers the electromagnetic and strong nuclear forces.
Even the atoms.
Atoms and subatomic particles are ripped apart. The chemical bonds holding molecules together snap instantly.
And then time 0.
Space-time itself shreds at the Planck scale.
What does that even mean physically?
The Hubble constant reaches infinity. The distance between any two infinitely close points in the universe becomes infinite. The concept of dimension loses all physical meaning. Reality is torn asunder.
The fabric of reality is torn to ribbons. Now, in the theoretical physics community, there's a physicist named Pedro González Diaz who proposed a wild idea about phantom energy.
Ah, yes. The wormhole hypothesis.
He suggested that phantom energy could feed a wormhole, swelling its throat up.
Yeah.
Could an advanced civilization use a rapidly expanding wormhole to escape the big rip? Just slip out the back door of the universe before it tears apart?
That is a highly speculative and ultimately futile interpretation of the mathematics.
Why not?
While it is theoretically true that phantom energy could enlarge the throat of a traversable wormhole, navigating it during a period where the fundamental scale factor of the universe is accelerating toward infinity presents insurmountable physics problems.
But if the door is getting bigger, why not drive a ship through it?
Because the tidal forces within the wormhole would be expanding just as violently as the universe outside. The geometry of the wormhole is still embedded in space-time. Attempting to traverse it would not save you. The spatial metric inside the wormhole is also being ripped apart. Traversing it would simply leave you in tatters in a different topological region of a dying cosmos.
So it's a meat grinder either way.
There is absolutely no escape from the metric itself tearing apart.
Okay, so heat death takes trillions of years. The Big Rip takes billions of years. They both give intelligent life plenty of time to sit around and dread the end.
To anticipate it, yes.
But there is a third scenario we need to look at, one buried in quantum field theory that could happen right now, today, while you're listening to this, with absolutely zero warning.
You are referring to false vacuum decay.
The swift assassin. Okay, let's get into the weeds here. How does this actually work?
It hinges on the concept of energy states in quantum fields, specifically the Higgs field.
The field that gives everything mass.
Yes. The Higgs field permeates all of space. Now, a fundamental rule of quantum physics is that a physical system always seeks its lowest possible energy state, known as the true vacuum or ground state.
Like water flowing downhill.
Precisely. Currently, our universe sits in what appears to be a stable vacuum state.
Appears to be.
Yes. Based on the measured mass of the Higgs boson and the top quark, our current baseline energy state might actually be a false vacuum.
Let's use an analogy here to make sense of this. Imagine you are hiking up a mountain and you find a little dip or a puddle on a ledge halfway up the cliff. Water gathers there. The puddle is stable, right?
It is in a local minimum.
A false vacuum. The true valley floor, the true vacuum is thousands of feet below.
A perfect analogy. In classical physics, the water stays on the ledge unless something physically pushes it over the edge.
Right.
But as we discussed earlier with the iron stars, quantum mechanics allows for quantum tunneling. A localized point in space, a single quantum fluctuation could spontaneously drop from our false vacuum ledge straight through the mathematical barrier and into the true vacuum at the bottom of the valley.
And what happens if one single point in the universe drops into the true vacuum?
It triggers what is known as the Coleman-de Lucia mechanism.
Which is what?
This spontaneous drop creates a bubble of true vacuum, a region of lower energy space. Because this true vacuum is at a significantly lower energy state, it is overwhelmingly energetically favorable.
It wants to spread.
The surrounding false vacuum will immediately begin converting into true vacuum. This bubble will begin to expand outward in all directions.
Expanding how fast?
At the exact speed of light.
This is the ultimate mindfuck of this entire deep dive. Because this bubble expands at the speed of light, no information can precede it.
It is physically impossible to be warned.
You could not see it coming. Our telescopes wouldn't detect a shifting distortion in the stars. Light from the edge of the bubble reaches your eye at the exact same instant the bubble itself hits your body. One instant you are listening to my voice, the next. Nothing. The fundamental laws of physics are instantly rewritten.
Indeed. The properties of elementary particles, their masses, and the strength of fundamental forces are dictated by the energy state of the vacuum.
So inside the bubble, everything is wrong.
Inside the true vacuum bubble, the physics that allow for the existence of atoms, chemistry, and biology would simply cease to operate. The electromagnetic force might change. Protons might suddenly become heavier than neutrons, causing all atomic nuclei to disintegrate.
You'd be instantaneously obliterated at the subatomic level.
Wiped from existence.
Just wiped from the chalkboard. But what is it like inside that bubble? Does it just become a different kind of universe with new, weird aliens and weird physics?
According to theoretical models, the interior of this newly created space would not be a tranquil, alternate universe.
Oh, it wouldn't.
No. The mathematics suggests that the interior of the true vacuum bubble would possess a massive negative cosmological constant.
What does that do?
The geometry of this space is known as an anti-de Sitter space, or ADS space.
Anti-de Sitter space.
Yeah.
Okay, what does ADS space do to whatever matter is left over?
An ADS space with a large negative cosmological constant is highly gravitationally unstable. The vacuum itself has a negative energy density that pulls space inward violently.
So it collapses.
Any matter or energy inside this true vacuum bubble would undergo rapid, catastrophic gravitational collapse.
Yeah.
The entire interior of the expanding bubble would crunch into a singularity in a matter of microseconds.
Jesus.
It is total, instantaneous atomic erasure, immediately followed by absolute gravitational crushing.
It's the ultimate executioner.
Yeah.
No pain, no anticipation, just off.
It is entirely governed by quantum probability. The tunneling event could happen in 10 to the power of 100 years, or it could have happened a billion years ago in a distant galaxy, and the bubble is sweeping toward us right now, arriving today.
I need to take a breath. Just, okay. Because as terrifying as vacuum decay is, all the theories we've discussed so far, the slow freeze of heat death, the violent shredding of the rip, the instant slurp of the vacuum decay, they all share one foundational assumption.
They assume a standard cosmological history.
Right, they all assume we live in a living universe that was born from a hot Big Bang and is currently expanding outward. But our final, most recent scientific framework completely shatters that assumption.
The paradigm shift.
What if that foundational idea is a delusion? What if we are already dead?
You are introducing the dead universe theory, or DUT.
Yes.
This is a radically divergent cosmological framework published recently, spanning papers from 2024 to 2026 by theoretical physicist Joel Almeida.
And it completely rejects the standard lambda CDM model.
It rejects our current consensus of an expanding universe originating from a hot, dense singularity.
It rejects the Big Bang entirely.
Yes. The dead universe theory asserts that the observable universe, everything we can see with the James Webb Space Telescope, every galaxy, every quasar, is merely a transient luminous anomaly.
An anomaly.
It characterizes our visible cosmos as a localized thermodynamic perturbation.
A blister.
Precisely, a luminous blister on the surface of a hypercosmic structural black hole.
Okay, wait, Rep.
According to this framework, this massive structural black hole is not the result of a collapsed star within our universe. Instead, it is a primordial remnant embedded in the true universe.
The true universe.
What Almeida terms the dead continuum, an ancient, silent, pitch-black continuum composed entirely of exotic dark matter, specifically particles known as axions.
So we are just a tiny bubble on the surface of a dark matter black hole.
In this model, gravity doesn't just work through the mass of objects bending space-time like a bowling ball on a trampoline. It is governed by topological gravity.
Okay, stop there. Explain topological gravity. How is that different from Einstein's gravity?
In general relativity, gravity is a local effect. Mass curves the space immediately around it. Topological gravity suggests that the overarching structure, the connectivity and shape of the entire universe on a macro scale, exerts fundamental gravitational constraints on everything inside it.
So the shape of the room dictates how everything inside it moves.
Exactly. In this model, the visible universe is not expanding outward into nothingness. It is a temporary energetic fluctuation trapped within the fixed, overwhelming topological geometry of a vastly larger, already deceased cosmological structure.
This is a staggering shift in perspective. To say that light itself isn't a primordial constant. Light, stars, galaxies, they are just a thermodynamic anomaly. It's the terminal fever of a collapsing system.
That is a very poetic but accurate summary.
But wait, if this theory is right, how does it explain the expansion we see? We look at distant galaxies and see them redshifting, their light stretching out, proving they are moving away from us. How does DUT explain that if not by an expanding universe?
DUT reinterprets the cosmological redshift entirely. It introduces the concept of asymmetric thermodynamic retraction.
Okay, let's look at the math for that.
The mathematics here are crucial to understanding the mechanics of the model. The theory models the net galactic generation rate using a differential equation. dN over dt equals n dot sub f minus n dot sub d.
Wait, hold on. Let's look at those variables. dN over dt is the rate of change.
Yes, the change in the number of active galaxies over time.
And n dot sub f is formation.
The birth rate of galaxies.
And n dot sub d is death. You're saying the derivative is negative. dN over dt is less than 0.
Mathematically, yes.
In biology, if the death rate outpaces the birth rate, that species is going extinct. Is this theory arguing the universe itself is an endangered species?
That is an apt biological analogy. The standard lambda CDM model assumes the universe is constantly generating new structures as it expands, but DUT argues that this derivative is strictly less than 0.
It's shrinking.
The extinction rate of active, luminous galaxies vastly outpaces the formation rate of new ones. The universe is not undergoing eternal metric expansion. It is experiencing what Almeida calls structural infertility.
The capacity of the cosmos to generate new complexity is rapidly degrading.
Yes.
It's going through cosmological menopause. It's losing its ability to reproduce stars, to build galaxies, and that redshift we see, the stretching of light.
Under DUT, redshift is not a Doppler effect of galaxies moving away through expanding space. Instead, it is an optical and thermodynamic consequence of this retraction.
So what are we actually seeing?
The apparent disappearance of galaxies at the edge of our observable horizon is actually a natural return to gravitational equilibrium. The matter is literally falling back into the event horizon of the underlying invisible structural black hole.
Let me make sure I'm visualizing this correctly. The metric illusion. When we look through a telescope and see things getting redder, stretching away, we think, space is expanding like a balloon.
The standard interpretation.
But DUT says, no. We are actually seeing the tension of a blister pulling tight, flattening out before it collapses back into the dead, dark corpse it grew out of.
That is a highly accurate conceptualization of the theory's gravitational mechanics. Gravity is drawing matter inward toward the curvature of the dead primordial body.
That is just chilling.
And the theory does not just state this conceptually. It derives a specific mathematically rigorous constant for this dynamic, termed the universal growth index, represented by the Greek letter gamma.
And what does gamma equal in this theory?
Gamma emerges from the characteristic equation governing this irreversible thermodynamic asymmetry. It equals exactly the square root of 5 minus 1, all divided by 2.
Wait, the square root of 5 minus 1 over 2, which is approximately 30.618.
Yes.
The golden ratio.
Correct. The golden ratio.
Okay, that is deeply unsettling. The golden ratio is a mathematical signature of nature. It dictates the spiral of a nautilus shell, the arrangement of leaves on a stem, the shape of hurricanes, and you're saying it's the exact mathematical decay rate of the cosmos.
In DUT, the golden ratio emerges not as an arbitrary parameter fitted to observational data, but as the asymptotic attractor of the perturbation dynamics.
The universe is decaying into the golden ratio.
It proves, within the strict mathematics of the theory, that the universe is naturally, inevitably returning to gravitational equilibrium. It is a geometric consequence of the viscoelastic vacuum dissipating its remaining energy back into the dark, silent structure. The universe is decaying with mathematical perfection.
The existential horror of this is absolutely peaking for me right now. If the dead universe theory is correct, we are living inside a cosmic cemetery.
The data supports the metaphor.
When the James Webb Space Telescope looks out into the deep field, taking those breathtaking images of glowing galaxies, it's not looking at the dawn of a vibrant new universe. It is looking at fossils.
The fossilized remnants of a dead system.
All that dark matter that astrophysicists have been searching for. It's not some mysterious, invisible scaffolding holding galaxies together. It's ash. It is the cold, dead ash of the true universe we are trapped inside. We are bacteria glowing on a rotting corpse.
The theory explicitly uses the term fossilization to describe this state, and the timeline it presents is drastically compressed compared to the standard heat death model we discussed earlier.
How compressed? We were talking about 10 to the power of 100 years before.
The timescale for complete energy exhaustion and structural collapse in the dead universe theory is calculated to be a mere 166 billion years.
166 billion years. Our universe is already 13.8 billion years old. Compared to the trillions and trillions of years in the 5 ages model, that is a blink of an eye.
It is imminent on a cosmological scale.
Uncomfortably imminent.
Within this relatively brief window, the universe will reach a state of irreversible structural dormancy. No new structures will emerge, the blister will flatten, and though mass and spacetime will technically persist, they will do so only as cold, dark components of the dead continuum.
Okay, let's unpack everything we have journeyed through today, because this is a massive, heavy burden of knowledge.
It is a comprehensive overview of our physical limits.
We started with the agonizingly slow freeze of the dark era, watching the last black holes evaporate into a sea of cold photons. We looked at the shredding, tearing violence of the Big Rip, where phantom energy literally pulls the Earth out from under us and rips our atoms apart.
A structural failure of reality.
We faced the silent, instantaneous execution of vacuum decay, where the fundamental laws of physics themselves turn against us at the speed of light. And we ended with the ultimate, mind-bending revelation of the dead universe theory. That we might not be the pinnacle of a thriving cosmos, but just the glowing rot on the corpse of an already dead universe.
Each model provides a rigorous, mathematically derived boundary condition for existence.
Whether we like it or not.
Exactly. Whether through the slow creep of entropy, expanding metric tensors of dark energy, quantum phase transitions in the Higgs field, or thermodynamic retraction into a structural black hole, the data unequivocally points to a finite duration for complex reality.
I want to leave you with one final thought to mull over. One that steps slightly away from the hard math and into the philosophical weight of what we've discussed today.
The existential implications.
Right. Back in 1875, there was a philosopher named Philip Mainlander. He looked at the concept of the heat death, which is the brand new science of thermodynamics at the time, and he didn't see it as a tragedy. He didn't view the end of the universe with the existential dread that we've been cultivating for the last hour.
Mainlander interpreted the march toward maximum entropy through a vastly different ontological lens.
He did. He proposed that what if the death of the universe, the total cessation of all motion, all energy, all life, all structure, isn't a disaster? What if it is the universe's ultimate redemptive destiny?
Redemption through equilibrium.
Think about it. Life is struggle. Complexity requires friction. Existence is defined by tension, by the desperate need to consume energy just to stave off decay for one more day.
Thermodynamic maintenance.
What if heat death is simply the final, permanent end to all cosmic suffering? A perfect, infinite, unbreakable peace.
A return to absolute equilibrium, a state where no further work is demanded, no energy must be spent, and no gradients remain to cause turbulence or conflict.
Exactly. So tonight, when you step outside and look up at the night sky, I want you to really look at the stars. Look at the darkness between them. And ask yourself, are you looking up at a thriving, endless cosmos? Or are you just watching the fading embers of a cosmic tomb, slowly, perfectly finding its way back to peace?